Electricity and magnetism are interrelated and are also interconvertible. Let us look at a few examples. In this setup, an electric current passing through a conductor produces a magnetic field, which can be observed through the deflection of a magnetic compass needle placed near the conductor. This proves that moving electric charges produce magnetic fields. Electric motors work on this principle. However, in this setup, we see that an electric current is induced in a closed coil when subjected to a changing magnetic field. The phenomenon in which an electric current is generated by varying magnetic fields is called electromagnetic induction. Electric generators work on this principle. We will now discuss and learn about 3 experiments by Faraday and Henry relating to electromagnetism. In the first experimental setup, a coil is connected to a galvanometer. When a bar magnet with its north pole facing the coil is moved towards or away from the coil, the galvanometer needle deflects to the right and left side of 0 reading respectively, showing the presence of a current in the coil. Now, let us see what happens if the south pole of the magnet faces the coil. The galvanometer needle deflects to the left side of 0 reading as the magnet approaches the coil and deflects to the right when the magnet moves away from the coil, showing the presence of a current in the coil. The galvanometer needle deflects only as long as the bar magnet is in motion. Once the bar magnet comes to rest, the galvanometer needle settles down at 0 reading, indicating that there is no current in the coil. From all these observations, we can conclude that whenever there is relative motion between a bar magnet and a coil, an electric current is induced in the coil. In the second experimental setup, there are 2 coils. Coil 1 connected to a galvanometer, coil 2 connected to a battery. Due to the steady current in coil 2, a steady magnetic field is set up around the coil 2, and this magnetic field is also linked to the coil 1. When coil 2 is kept stationary and coil 1 is moved towards coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the left of 0. When coil 2 is kept stationary and coil 1 is moved away from coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the right of 0. If we keep coil 1 stationary and move coil 2 towards coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the left of 0. Now, if we keep coil 1 stationary and move coil 2 away from coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the right of 0. From all these observations, we can conclude that whenever there is relative motion between a current-carrying coil and a closed coil in which a galvanometer is connected, a current is induced in the closed coil. In the third experiment, a tap key is provided in the coil 2 circuit. Here, we can observe the deflection of the galvanometer needle even when the 2 coils are stationary. This deflection is observed only at those instants when the tap key is either switched on or off. This happens because of the change in magnetic field during switching on and off. When a ferromagnetic material like an iron rod is placed coaxially along the two coils, the effect of the magnetic field linked to the coil 2 increases due to the nature of the ferromagnetic material, as it allows more number of magnetic lines of force to link within the area of the coil. Hence, the deflection of the galvanometer needle increases, indicating an increase in the induced current.